How's it going?
All right.
Good. Good. Does anybody have questions from the homework that they'd like to look at before we go on? Yeah.
Yeah, on the chapter 2 homework, I was wondering why there's a question on there that has like 34 parts to it.
34 parts? Maybe like 10? 8?
I'm pretty sure it had 34.
Which question is it?
I don't know.
It can't possibly have 34 parts.
It had a lot of
Literally 34 parts.
It was a lot of parts.
I got it.
It was towards the middle of the thing because I worked towards like
It was what?
8.
Which number was it?
Started at the end of it and worked backwards.
Which number is it?
That one right there. See?
Oh. Yeah, but I mean, to be fair, like, that's a small 34 parts.
Everything else is like 2 parts, like maybe 8 at most.
What are the 34 parts? Just inputting the numbers?
Yeah, I mean, you're building a table, so like each line is a new part, right? So like 0 to what? 0 point something, whatever, 5, and then you're figuring out how many are in there, right? Is that true? Yeah. You know, you could probably do this in StatCrunch. I bet if you open this data in StatCrunch. Let me just see if that's true, because they give you all the numbers in order, and I think you can make a frequency distribution under, is it a chart or is it, what is it? I don't usually do frequency distributions on here. Is it under tables? Yeah, there you go. So under a frequency table, if you click that variable and say you want like a frequency distribution, I think you can do the bins. Oh, maybe it's going to try to bin it. I don't know if you can actually do your bins. I thought it would let you pick your bins, like how wide you want to go, you know? Let me see what it does. Whoa, lots of unique numeric values. Want to turn on a binning procedure? Yeah, I do want to turn on a binning procedure. Yeah, so there you go. So I think you can, well, where did, it said it want to turn on a binning feature, but why didn't it? Does it not let me edit my bins? Yeah, it did bin it, but I thought it would let me pick my bin widths. Usually it does. So, I don't know, actually. Maybe not. Anyways. It's not, I mean, I don't know. It's not terribly, I don't think it's that terribly difficult to bin them up. But you could also get around it by doing a histogram, because in the histogram you can actually bin them. So start at 0 with widths of 0.5. And if you were to compute it, then you could just look at the frequency here. See, so it actually tells you that there's 9 there, and there's here's why is it taken away? What the heck is turning pink? But yeah, you can actually see the types. That's 9. You know, this is 4. This looks like it's 5, 4, 3, 2, 2, 1. So you could kind of make the histogram and get the numbers off of there pretty quick too if you wanted. That's another way, or you could just count them up. But yeah. Anyways, there's a couple ways to do that. But it's mostly making tables, yeah, and then you turn into relative frequency, right? So, is there more than one with 34 parts on it, though? I don't know about that. Oh, just leave me that. Whatever. That one only has 1. Yeah, I think that was the only really one, because you have to actually make the tables. Yeah, so I think you can handle it. I mean, since this is a math class, right, if you skip one problem out of 38, what does that really do to your grade? I mean, it makes it not 100, but it's a percentage of a percentage of a percentage, right? Because it's only a percent of homework 2, which is only a percent of your homework grade, which is only a percent of your overall grade.
Could be the difference between passing and failing if it gets down to it.
It could be. That is absolutely correct. I mean, granted, I usually round your grades, you know, and I never round down.
By 10?
Huh?
By 10?
To the I round to the nearest 2.0.
Yeah.
No. Anyways, any other questions besides or complaints? I take them all.
Wi-Fi.
Student Wi-Fi. That was a common complaint in my 107 class. We did a student survey. Wi-Fi and parking are the two services that most students are dissatisfied with. But
Most of your work is online. Wi-Fi is a big,
So.
very big complaint.
yeah, the Wi-Fi. Okay. Any other questions about the homework or anything like that? You guys want to ask? Okay. I did put so I put up our next activity that I want you guys to work on for next week. And it has to do with some of the things. I'm going to change the way I'm going to take submissions this time. I put in a new folder here for activity submissions. So rather than emailing them to me, because I was having second thoughts about that immediately after I received my first 25 emails, you can just upload documents straight into this activity submission. And you can just pick whether it gives you an option between like private or instructor only or entire class. So just pick instructor only access if you don't want anybody else reading your assignment, or let everyone read it if you want. It's up to you. But anyways, just drop them into this folder from now on. Okay, activity submissions. And then I'll pull them out from there at the end. It's easier for me to do it that way. But I did put the new activity into, because people were dropping them in here and it's kind of getting cluttered for me. You won't be able to see that one when you log on. I'm the only one that can see it. But this is a new one. So this one I want you to try. I want you to do something else. Okay, so we figured out some strategies for sampling in chapter 1, and then from your percentage of trucks on the road. So now what I want you to do for me is I want you to estimate the average value of the vehicles of CVC faculty, staff, and students. That's what I want you to do. Okay? So I want you to, the average value, so like the average sale price, like what the cars are worth. So I want you to estimate the average worth of CVC faculty, staff, and student cars. Okay? Any questions? Right? So you get to choose. Yeah, I mean, you get to choose how you want to. You get to choose how you want to assign values to cars. Right? You get to choose how you sample the cars. Right? That's your choice. So you get to decide how to do the sample. You get to decide how to calculate the value. But I want you to do what?
If we get
What's up?
approval for prowling, are you going to bail us out?
Well, what are you going to be? How in detail?
Pictures of cars.
I don't think you have to get in cars to estimate their value. Right?
Check the mileage.
Yeah. What features?
I'm taking no responsibility for any criminal charges that may result. So, yeah, that's true. So you can choose. You can take surveys of people themselves, or you can actually go out and look at physical cars. It's however you want to do that. Okay? And so part of that, what I want is I want an estimate for the average value and the standard deviation. We haven't talked about standard deviation, but we're going to talk about that probably today, if not tomorrow. And also, I want you to make a nice graph. So this would be a good opportunity to start using StatCrunch. You can make the graphs by hand if you want, but you can also make them really easily in StatCrunch, which we're going to see today. Okay? So this would be a good opportunity to get kind of used to that. And they always are prettier when the computer makes them anyways.
How much is your car worth?
My car?
Yeah.
Well, I have two cars. No, I probably have one that's only worth about $4,000. So
Is surveying personally enough for this activity?
that's up to you. But that's just my estimate. I haven't blue booked it recently. So I have no idea what my other car is worth. So
What kind of car is it?
it's a Toyota Sienna. It's pretty badass.
Is that the toaster?
No, it's a van. It's Toyota's van.
Well, yeah, but what's your other car? You have like a toaster, don't you?
No, I have a little Yaris.
Well, yeah, toaster.
Is that a toaster? I thought the toasters were those Scion boxy card things. Right. Mine looks more like a little bean or something. It's not very attractive. But it gets 40 miles a gallon, and I've never had to service it or anything. So, I mean, I changed the oil in it, obviously, but I've never had like mechanical problems with it. So,
Just 'cause you said that you're going to now.
yeah, this isn't probably Whalewood, but okay. Anyways, yeah, you can use mine, but you might want to blue book it because I don't know if it's actually worth that. It's probably worth like $1,000 or something. So,
What year is it?
it's a 2008. So there you go. You can start right now. It's a 5-speed hatchback. So it's like the cheapest one you can possibly buy.
Other coffee.
So, what? You think I have leather seats in my Yaris? Okay, we're moving on. Okay. So, anyways, that's your job. Okay. So come back. Come back on Monday with data and maybe some graphs and some estimates. We're going to talk about the actual how to do graphs in StatCrunch and that mean and standard deviation. I'm also going to show you how StatCrunch can calculate that stuff too, which will help you in homework or chapter 3 homework. Okay. Yeah, bring it back Monday. Next Monday. Okay. All right. So, in the meantime, I lost my annotations from yesterday, so sorry about that, which also means I don't really remember where we were. I think we drew a pie chart and we drew a bar chart, and then we were talking about making, taking the quantitative data and turning it into distributions or histograms. Yeah. Is that true? So yesterday we were looking at this one. Is that true? The limits to maturity. Okay, and this is kind of where we left off. Is that true? Okay. So we had picked the minimum was what, 10 to 90, was it 99 days? Where is that 99? Oh, there you go. Thank you. So the range was basically 10 days up to 99 days. And so we were going to split this into groups. And I had told you, you can kind of pick your bins appropriately, but typically you want 5 to 10 bins. So that's how you want to split up your range. In this case, the range is 90. So we could split it by 10s. That'll make 9 groups, 9 classes. We could also split it by 20s, and that would only make 4 classes. So it'll change the way your frequency works. So it was days. So you could do I think yesterday we were looking at the 10, weren't we? So 20 to 29, 30 to 39, 40 to 49, 50 to 59, 60 to 69, 70 to 79, 80 to 89, and 90 to 99. So that would be maybe if we wanted to split it into bins of 10. We could also go the other way, and we could split it into, say, 20s. So we could go like 0 to 19, 20 to 39, 40 to, what would that be, 59? 60 to 79, and then maybe 80 to 99. We could split our bins that way as well. It doesn't really matter. One's going to give us, one's going to be a little bit simpler. One's going to give us a little more detail. Okay, my thing is wobbly. It's just bugging me. There we go. What does that mean?
So is this the histogram?
So this is a frequency, but we're going to turn it into a histogram. Yeah. So typically you turn it into a frequency, and you just take that and make a histogram, similar to how we turned frequencies into bar charts before. So then you just got to go count up. So I'm going to need your help. So let's go back here. How many were between 10 and 19 days? So how many were there? There's 1. Was that it? Do you see anything below 19? I don't. Okay, so there's only 1 there. Okay, go and look at how many were in the 20s. So where do you see them? Do you see any in the 20s? I don't see any in the 20s. So there was 0 there. If you go to the 30s, how many were in the 30s? 1, 2, anything else? 3. Did I get them all? Is that all of them? Okay. Whoa, where am I going? Go the right way, Ryan. 3. Let's see how many were in the 40s. So that would be going around. Do you see any? I see 1. So I see 1 there. So only 1 in the 40s. You go to the 50s. So that's 1. What else? 2, 3, 4, 5, 6, 7, 8. Do we get them all? Okay, so 8 in the 50s. Then we go for the 60s. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 in the 60s. So I think we got all the 60s. Then you go to the 70s. So that's 1, 2, 3, 4, 5, 6, 6 in the 70s. Then you go for your 80s. So that's a 1, 2, 3, 4, 5, 6, 7. So that's 7 in the 80s. And then finally, you clean up with your 90s, and that was what, 1, 2, 3, 4 left over for your 90s. There you go. So you got your frequency. So you split them into bins, and you figure out how many are in each bin, right? We could condense this really easily now. We already got our data. How many are between 0 and 19? Well, there's just one. How many were in the 20s and 30s? 3. I'm just combining these numbers. The 40s and 50s were 9. The 60s and 70s were 16, and the 80s and 90s were 11, right? I think what we're going to see is when we turn it into a histogram, I think this one's going to give us a nicer histogram, probably, is my guess. All right, but it doesn't really matter. But I tend to do closer to, I tend to like closer to like 8 to 10 bins rather than 4 or 5. Right? Okay. You guys cool with that? Make sense? Just make sure that your bins are equal width. That's the key. All right. So once you do we do that? I don't want to use that one. So once you have that nice frequency distribution right here, then that's what you're going to take and turn into a histogram. So I'm actually going to skip some of these examples because I think I put way too many examples on there. What? Delete. I don't want that. Why not? Oh, there we go. This is the one I want to do the histogram of. Okay. So once you take that to turn into a histogram, then you're just going to draw on the x-axis, you're going to draw your class widths, and on the y-axis, you're going to draw your frequency. So for the first example, okay, we're just going to cut our class. Our class widths picked up at like 10, didn't they? 20, 30, 40, 50, 60, 70s, 80s, and then the 90s, right? And they all run up next to each other, right? Because all this data is occurring on a continuum. And then you just draw your bars to the right height. So our bars go up to 10, it looks like. So we go maybe 2, 4, 6, 8, 10. So in that first bin, in the 10 to 19, there was only 1. So our bar would go up to 1. There was nothing in the next bar, right? There was 3 in the 30s. So this bar would go up to 3. There was 1 in the 40s. In the 50s, there was 8. So that bar is going to hop up to 8. Yeah. In the 60s, there was 10. So that's going to be our biggest bar. It's going to hop up to 10. Then in the 70s, then 6, then 7, then 4. So 6, then up to 7, and then down to 4. Yeah. That's a histogram. And notice that the bars touch as opposed to a bar chart. And it's significant because, again, remember in the bar chart, like with political parties, there was no reason we had to put any particular political party in front of the other. You can mix them around. They're categorical. But in histograms, right, it wouldn't make any sense to take this bar in the 60s and drop it down here below the 10s or something, right? So the bars touch because the data runs up against each other, and it's in order. The other thing you see here is that you're starting to get at what we call the shape of a data distribution. So what do you notice about the observations for the days to maturation? Remember, this was how many days it took for investments to mature. So what do you notice about these investments? Like the spread of the days.
Kind of peaks towards the middle.
Yeah, it kind of peaks right here around days in the like 60s, 60 days-ish. That's where you see the most people. What else do you notice?
After that, it drops off.
It drops off pretty quick. What else do you notice? Anything else you notice about it?
The huge jump between 40 and 50.
Yeah, so notice there's hardly anything down here. It happens every once in a while, but there's just not much down there. You can almost kind of like start to get this idea of like the way the whole distribution is shaped. And probably if we looked at more and more of these investments, we'd probably see the pattern continue to go that way. All right. So we're going to start talking about shapes of distributions as well. All right. But it tells you basically the bulk of the investments are up here in the 50 to 100 days. You see some that mature really fast. It's just not very common. And you really don't see anything out here beyond 100 days. Okay? All right. Any questions about that? How to make a histogram? You guys feel pretty good about that? Everybody do that? Great. All right. We didn't do that example, blah, blah, blah. Okay. So, this is my old book slides, isn't it? This is stuff that we want to get to. This is stuff we're going to hit in Chapter 3. So forget about that junk. Boom. Done. Hey, that was easy. Chapter 2 is done. Yeah, your other book puts that other stuff off to Chapter 3, which I have the slides for, so we're going to go to. All right. You can make these. I want to show you how to make this in StatCrunch. So let's say we take these, this data. I want to say I can copy, but I tried this before, remember? And you guys watched me try to learn how to copy paste for a few hours or minutes or whatever it was. But I will show you. Actually, I kind of showed you on that last example. I might pull that one back up. So you can always open, you don't have to open it from your homework. You can just click on that StatCrunch button on My Math Lab and just go to the StatCrunch website. The book has some data sets built in. If you click that, it's going to take you there to the actual data set. So there may actually be some data in here that corresponds with some of the chapters that we just looked at. I don't know. Let's see what this data is. So like this shows you the diameter of something. I don't know, a bunch of diameters. But if you open it yourself, you can get there. What happens if I do this? Oh yeah, remember it did that to me before. Yeah, I can't paste it in there. But I can just copy the numbers because it won't take that long. So our days of maturation were 70, 64, 99, 55, 64. And I covered them up so they're hard to read now, so that's really awesome. What was that, 39? Or was that 89? I can't even remember. I'll probably make a mistake, but that's okay. It's just for display purposes. So okay. So there's all our data. When you're in StatCrunch, you go into graphs. This is where you can actually make bar charts. You can make pie charts. We're going to go with the histogram. And so you just pick the column that your variables are in. So it's all there in variable 1. We started our bins, for example, at I think 10, didn't we? And we did bandwidths of 10. So we cut it off every 10. And I think if we compute that, yeah, theirs should look a lot like ours, yeah? Does that look like basically what we came up with?
Yep.
More or less? Ish. So basically the same kind of graph. Yeah? Cool. So it'll do that for you. So you could use that in, say, your activity. If you get a whole bunch of values of cars, then a histogram might be an interesting thing to look at because it kind of shows you where the distributions lie. Okay. All right. Cool. So again, that's in graph histogram. Yeah? Cool. All right, there's also tutorials on that if you want to look at the, I showed you there's those videos and tutorials. And I think, I don't have one for graphs. I might have to add one. All right, so let's move on. We want to go to chapter 3 now. Okie dokes. Got it. All right, so what we just talked about were examples of graphical summaries. The moral of the story basically is that if you have categorical data, you stick to pie charts and bar charts. If you have numerical, quantitative data, then you go with the histogram. But there's also ways that we can do numerical summaries. And we talked about some examples of these, right? So in a numerical summary, the whole idea is you're trying to come up with a single value that describes your data. Okay, so rather than making someone look at a big long list of numbers, let's just give me just one number. Maybe give me 2 numbers that tell me enough about the data so I know it without having to actually see all the numbers. That's the idea. Okay, so in chapter 3 we're going to be covering some of the more common numerical summaries. Okay. There's typically two types of numerical summaries that or three types actually, we're gonna look at this book. So let me add that here. So the three types we're gonna look at is we're gonna look at measures of center. We're gonna look at measures of spread, or I think your book calls it. What word do they use? I can't remember what word. Dispersion. They use the word dispersion. Sometimes it's called variability. And then we're also going to look at some measures of relative standing. Not bellative. How about relative? We'll go with that. So those are the three we're going to look at. So we'll look at some things. So the measures of center, it's kind of like trying to give you an idea of like, where's the middle of these people? Where's the middle of these values? The spread is kind of like, are things really spread out? Or are they kind of condensed? And then the relative standing is going to help give us information about, say, where you stand in relationship to the rest of the population or the rest of the sample. And all those are going to become pretty important to us as we move on in this class. Okay, so your book calls the measure of central tendency. That's just measures of center or middle. Okay. What are some measures of central tendency or measures of center that you've heard of? And we kind of talked about some of these yesterday. What's one value that could tell you something about the middle of a data set?
Like the average?
Yeah, so the mean or the average is a very common measure of center or central tendency, right? You average everyone up. In fact, that's what I'm asking you to do for the value of cars, right? Why don't you average them?
Oh, you said median.
Yeah, the median is another one. I didn't ask for that in the activity. I probably should have. But that's okay. Okay. That's okay.
The mode.
And yeah, and there's another one that's commonly called the mode. We don't really, so in statistics, we don't really use the mode that often, but it is a measure of central tendency because typically wherever your data is, if there's observations that occur most commonly, they're probably around the center of your data. Not necessarily. So, and we're going to focus mostly on these two. The mode is just the most common observation, right? So it's just whatever value pops up more often. So if I were to ask everybody's ages, then whatever age is most common among students, that would be the mode. All right? We're going to focus these two. The mean is what we're going to focus most heavily on throughout as we go through the quarter. But we're going to talk about the median too, because the median can be really important. All right. So the mean, the average. How do you find the average? Yeah, right. So the mean is just the sum of all the observations. And then what do you do with that sum? You divide it by, yeah, however many observations you take, right? So we use a little n to denote sample size, right? So you just add up everything, divide it by the number of observations, easy peasy, no problem, right? Okay. So probably all of you calculate an average at some point in your life, I'm assuming. In statistics and math in general, as we start to get into some more complicated formulas and things that involve adding a bunch of values up, it's kind of a pain to have to write out in words every time you want to talk about adding a bunch of things up. So we came up with a notation that we use in math called summation notation. So what we use is, if I want to say that I have I want to sum up a bunch of X values, okay? So you go out and you collect some data, right? And for, here's car 1, right? And maybe the value is X1. And for car 2, their value is X2 all the way up to, the nth observation, right? So these are what we call subscripts. And they're indices. They just track what value you're at. So that's the first car you looked at. That's the second car you looked at, all the way down to the nth car you looked at. All right? And so if I want to say sum up all of those x values, the way we write that is we use a big sigma. Okay? And the big capital sigma means sum. And next to the sigma, you tell me what you're going to sum up over. And I'm going to sum up the x values. Okay? Technically, in sigma notation or summation notation, we would tell you where the indices go. So in this case, it would go from 1. You start at x1, and you end at xn. So you say I start at the first value, I end at the nth value. If you just wanted to add up like the first 3 values, this would be a 1 and this would be a 3. That would say add up the first 3 x values, right? So, right, if I wanted the sum as I goes from 1 to 3 of the xi's, that would be x1 plus x2 plus x3, right? The way this is written, that would be x1 plus all the way out to xn, right? I'm saying add up all those x values, okay? So we use that sigma notation, and the way it works for us for the mean then is another way that we could write this definition of the mean is we could write that as the sum of all the x's divided by n, right? A lot of times we don't include the indices in statistics because it's assumed that you're just going to do it for all the values, right? It wouldn't make sense to only calculate the mean on maybe 3 of your values. You do it on all of them. Okay, so this is another notation we use. And we're going to be using it again when we talk about standard deviation. All right? So that's summation notation. Any questions about that? About what any of the things mean? No? Okay. So we do also use a little bit of notation to differentiate whether or not we're talking about a population mean versus sample mean. So in the population, we typically say that the population is of size capital N, and we say that the sample size is little n. Okay? So you'll see that distinction in the book. And remember, this whole idea here, we talked about how in the big picture of statistics, right, you have a population. You don't have to write this again, but I'm going to rewrite it. From there, you take a sample. From the sample, you get statistics. Those statistics are estimating parameters, right? And those parameters describe that population for you. And so for when we're talking about the mean specifically, there's the parameter, and then there's the statistic. Okay. For the parameter, the population mean, we denote with mu. It's a lowercase Greek letter. And for the sample, we use an x bar. So mu is the population mean. And x bar is the sample mean. Okay, so these are just some notations we use. So if we could, which value do we really want to know? Which value are we actually interested in knowing?
The mu.
Well, yeah, the mu is what we wish we knew, right? Because that's the mean of the entire population. I really wish I knew the actual average value of every single car owned by CBC faculty, staff, and students, right? That's the true mean, that's the mu. The problem is that that's a parameter, right? The problem is it's unknown, and so the best we can do is we can estimate it with a statistic. So the x bar, that x with the bar over it, the sample mean is all we're ever going to actually see, right? The best we can do is just take a really big sample of cars and get that average and hope that it's close to the true mean. Yeah? Okay. Cool. So, example, you got a bunch of, so you go out, you take the data, and you look at the pulses of a bunch of students, and you want to calculate their average pulse. So what's the average pulse of these students? So how do you do it? The average would be what? Say this is a sample. You just add them all up. And then what are we going to divide by here? 9. Okay. Anybody got a calculator? Because I don't know the answer to this problem. You guys should pull out your calculators. That way we can get multiple answers. So tell me when you get an answer. And tell me what you think the average is. I'll take multiple answers until we get the same one. So add them up, divide by 9. What do you get? You got 70.8. Anybody else get that? Any others for 70.8? Anybody get something different?
I got
74.2, 74.2 going twice, 74.2. Get 74.2 going 3 times. I like that better. See, I just got to take a large enough sample size and we'll get it right. So 74.2 beats per minute. Yep. All right. Means pretty straightforward. Not too bad. Alrighty. So the other measure is the median. How do you calculate a median? What? So first you got to order your data, right? Small to large. And then from there, what do you do? Yeah, and it actually kind of depends. So if you have an odd, actually I should just say in odd because that's going to be easier for right. So if n is odd, then you just pick the middle number because there will just be a single number right in the middle. But if n is even, what do you have to do? Yeah, you average the two middle numbers. Which, of course, if you're averaging two numbers, that just means add them up and divide by 2. Okay? Okay. So odd's pretty straightforward. Just pick the number. Even's really not that hard either. Just take the middle 2 and throw them in there. All right. This is a median. So we can look at the same data set here with the pulse rates, and we could calculate a median. So the first thing we need to do is order this data. So I would reorder it and say, okay, that's 60. Is 60 our min? Yeah, 60, 60 again. Then what comes next? A 72. We got a 72, 73. Okay. 80, another 80, and 81. And then 86. Like that? Did we get them all? 1, 2, 3, 4, 5, 6, 7, 8, 9. Cool. And is this an odd number, right? It's an odd number. So you go in 1, 2, 3, 4, 1, 2, 3, 4, and boom. There's a number right in the middle. So that's nice and easy. Okay. We don't really have a symbol for the median just because we don't use it as often. But this is in beats per minute. Okay. There are some books that use a symbol for median, but I rarely do. Okay. Pretty easy? All right. Perfect. Now, what I do want to consider, though, is suppose that we took another sample, right? Let's say that we took another sample here, and that person had a pulse of 49 beats per minute. Okay. So, would you say someone with a pulse of 49 beats per minute is pretty representative of most people? No, probably not. That's probably a little low. Not many people have pulses that are under 50 beats per minute. So this person is kind of a little unique. What I want to do is I want to see what happens when you add a value like this to our data set, right? So in our so if we were going to recalculate the mean, for example, so now we're going to add up all these values, but instead now we have to tack on that extra 49. And now how many observations do we have? 10. Okay. And what's going to happen to the mean if you tack that value on?
It's gonna drag it down.
It's going to change it. Let's see how much. So calculate that, and remember, what was it previously? 74.2.
Yeah.
Okay. So if we calculate the mean again, what do you guys get as your new mean? $71.7. Anybody else? Anybody get something different? I got some other 71.7 nods over here. 71.7 twice, 3 times.
Oh,
Okay, 4 times. I'm okay with that. So 71.7. Okay, beats per minute. Okay, and it was 74.2, right, before. What happens to the median, though? So if I go back to, say, here, right, and if I tack on a 49 down here at the bottom of my data set, right, well, now what happens to my data? It's even, so now I'm going to have to split the difference between these two values. And so the average of 73 and 76 is what, 74 and a half?
Yeah.
So the median comes to 74 and a half, whereas it was previously what? Was 76, right? So what happened to the mean? How far did it come down? About 2.5 beats per minute. How far did the median come down? Only 1.5. What if it would have been more? I mean, it wouldn't make any sense for this context. But what if this person's pulse would have been like 7 beats per minute? I mean, that person wouldn't be alive. But what if it was, right? Think about what that outlier would do. What's that going to do to your mean?
Drag it way down.
It's going to drag it way down, right? But what's it going to do to your median? It's going to be the same, right? Because whether this number's 49 or 7 or 0 or negative 5,000, right? You're still only going to have to average these two numbers. And so the median is going to stay the same. So the magnitude of that like really low-lying observation or one really up high, it doesn't have as big of an effect on the median as it does on the mean. The mean is a lot more sensitive to those types of observations. We call those types of observations outliers, typically in statistics. So an outlier, most of you have a pretty conceptual idea of what an outlier is, but it's basically just like an observation which is not representative of the population. Okay. So it's just somebody who's just really, really unique and just not representative of the population as a whole. Okay. Make sense? Right. So if you sample a car and you come across a car in the parking lot that's like a Tesla or something, right? That's not very representative of most CBC students, faculty, and staff. So that would probably be an outlier. When you come across outliers, typically usually you want to consider whether or not you even want to include them in your data set. You know, we'll talk more about that later. But sometimes you would want to include the outliers, and sometimes you really wouldn't want to include those outliers. So, anyways, all right. So then the idea that the concept we were seeing here with the median is that the median is something that we call resistant, or sometimes another word we'll use for that is, oh shoot, I can't even think of the other word, and I read it in the book, and then now I can't remember the other way. It doesn't matter because your book calls it resistant. Okay. So resistant statistics are relatively unchanged by outliers. I'll say outliers and extreme observations. I remember the word now. Resistance is a good way to describe it. In statistics, a lot of times the word we use as statisticians is we use the word robust. It's a robust statistic, so it handles itself well against outliers. So the median, which one? Sorry. Resistance statistics are relatively unchanged by outliers and extreme observations. So some of that doesn't look exactly like it's supposed to look like. But so as an example, the median is an example of a statistic which we consider resistant. The mean is not. The mean is wildly affected by outliers. Okay. And the bigger that value gets, or the smaller that value gets, the more it affects your mean. All right. So now this is going back to what we were talking about, shapes, data distributions. We did see some with that financial data. It had kind of a shape to it. The most common types of data distributions we're going to deal with is symmetric distributions. And within symmetric distributions, so symmetric distributions could really be about any shape. So they could be, maybe something like that. Anything that has symmetry, so they really could just be very flat. You could have data that's bimodal or something, right? Symmetric just means the same on both sides. But we're going to be, in statistics at least, what we're most concerned with, the most common symmetric distribution is what we call, not normal, but maybe normal. Normal, or sometimes you've probably heard it referred to as bell-shaped. And that's that nice distribution that's really high in the middle. It tapers off on the end, and it's nice and symmetric. Okay, so symmetric could be lots of things. We'll concern ourselves mostly with normal or bell-shaped. And what types of data, what types of values do you think probably have normal distributions, or do you know have normal distributions? So things you can measure out, people or stuff.
Prices of cars.
You think prices of cars might be normally distributed? It could be. Yeah, probably depends on the population. Probably at CBC, it probably is pretty normally distributed. Depending on where you went and took samples on, it might not be that normally distributed. But probably at CBC it is. What else?
Location?
What do you mean by location?
Like,
Remember, this has to be numerical data, like quantitative. So it has to be numbers you're measuring.
like the average income of a household?
Ooh,
Location?
good question. Do you think incomes are bell-shaped in America?
No.
Okay, so you don't think they're bell-shaped?
Well,
No? It all depends. Good answer. You'd make a great statistician. I don't think they are. I think they're another type that we're going to talk about in a second. Why? Does anybody know why I would think that incomes are not bell-shaped in America?
I feel like they're slope shaped. Like,
There's more low income and middle income than wealthy.
Yeah, so I think incomes in America are actually pretty skewed. Most Americans are earning, as if you look at singles, for example, most Americans are probably earning less than $100,000 a year. Almost all Americans are probably earning less than $500,000 a year. Wouldn't you say? A few people are earning a lot more than that, though. So I think it's probably skewed. But we'll talk about that in a second. So I don't think incomes are. What other values could be, though? So that's a good example, and we're going to come back to that.
Height of a person.
Yeah, so heights are pretty normally distributed. Obviously within the same gender, right? So you just look at female heights or male heights. They are pretty normally distributed, right around the average. Tapers off pretty quick. You don't see a lot of really tall people. You don't see a lot of really short people. Okay. Anything else you can think of that might be normally distributed?
Maybe lifespan?
Lifespan. It probably is. It could be a little skewed just because we have an upper limit on our lifespan. So you probably see a large chunk of people living to their 60s, 70s, 80s, tapers off around 90. But you do see, I mean, there are plenty of people who do die before that age, so it could be a little skewed. Actually, keep that one. That's a good example, I think, of one of the other ones. It's probably pretty normal, though. I think it's a little skewed. Anything else you can think of that could be normal? Of? Where?
Oh, yeah.
In college? Think it's normal? Do you think the ages of students at CBC are normally distributed?
I think there's a good chunk.
I don't think so.
I don't think it's CBC.
You think so?
Yeah, I think there's a lot of running start in high school students. Like that's like the majority.
Okay. So that means most people are down at the lower end of ages? What about people who are 30, 40, 50, 60, 70? Do we have those people at CBC? Sure. We have plenty of students. Well, I mean, are there a lot of them, though? So do you think it's probably normal? Remember, normally distributed means that the bulk of your data has to be right in the middle and it has to taper off evenly. But I don't think the ages of CBC students tapers off evenly. Because you have this lower limit where we don't really have anybody under maybe 15 because we're running start. That's as low as we go. And then kind of everybody, most of our students are probably below what age? What'd you think?
I would say 40.
Yeah, you say maybe even probably once you get into about 35, 40, you start to taper off pretty quick. But there's plenty of students who are in their 40s, 50s, and 60s. There's just not as many of them, I think. So that's another example of, you guys are really good at finding skew distributions. I like that. You can't think of anything else that might be normally distributed? Or you just don't want to say anything because I keep telling everybody they're wrong?
Times the class gets out.
Times that classes get out. I also think that's wrong too because the reason I don't think that is because we have more classes in the morning than we have at night.
No, I meant,
Or in the afternoon.
Length of class.
Oh, length
Like
of classes.
5 minutes.
Like how long class actually lasts.
Exactly.
Yeah, that's probably normally distributed, especially within maybe an instructor or even in general. Yeah, most classes probably last an average of,
An hour.
58 minutes. Yeah, so I think so. So class lengths probably are something like that. If you only keep yourself within classes that are scheduled to be an hour, right? That's probably pretty normal. Things I was thinking of are things like standardized test scores. Standardized tests are built to have normal distributions. So SAT scores, ACT scores, those have nice normal distributions. Lengths of pregnancies are pretty normally distributed among American women. Things like that. Okay. There are what time is it? Oh, we're like pretty much out of town. So we'll finish off these shapes tomorrow. So keep some of those other data sets in mind for tomorrow. And go ahead and start thinking about your activity and ask questions if you have them, okay?